Assalamu alaikum and welcome to lecture number 32. In this lecture we are going to discuss going to do the inverse Laplace transform and properties of the Laplace transform. We'll do few numericals on inverse Laplace transform, and then we move to the properties of the Laplace transform. The equation or the formula to find the inverse Fourier transform is as given here. We will not go into its derivation, but straight away we will use it, right? So if you compare with the Fourier, so you see in case of Fourier inverse transform, the scaling factor was 1 by 2 pi, and here it is 1 by 2 pi j. And in the Fourier case we were integrating it using limits of minus infinity up to infinity. So here we are using sigma plus j infinity and sigma minus j infinity. If you recall, in case of Fourier we didn't have the real part, so it was just from minus infinity up to infinity. So let's straight away start with an example. So we are given a signal x of s, and this is equal to 1 over s plus 1 into s plus 2. So we need to find the inverse Laplace transform of the signal to obtain x of t. So we can split it into two parts using the partial fraction expression. So it can be written as, if you recall, I think you have done in mathematics also in FSC, how to use the partial fraction expansion, right? So I just straight away write it. So to solve for a, we can write a equals to s plus 1 times the x of s. So this is 1 over s plus 1 into s plus 2 evaluated at s equals to minus 1, right? So s plus 1 cancels with this one, and when I replace s with minus 1, I get minus 1 here. Minus 1 plus 2 gives me 1, so 1 divided by 1 equals to 1, so that means a equals to 1. Similarly for b, I can write s plus 2 multiplied by 1 over s plus 1 s plus 2 and evaluated at s equals to minus 2. So s plus 2 cancels, and when I replace s with minus 2, so I get minus 1. So that means we can split it using partial fraction x of s, and we can write it as x of s equals to 1 over s plus 1 minus 1 over s plus 2, and the ROC is right here now that it's equal to real of s, and then this should be greater than minus 1. Now, depending upon the value of ROC, this can be right-sided or left-sided, both. I mean, this can also be right-sided or left-sided. You know, the algebraic expression is not sufficient. Okay, we also need the ROC to find the inverse, because while we were doing the Laplace transform, so you know that two different signals can have same mathematical or algebraic expression, but they will not have the same ROC. So you have done example something like this, you know that e power minus at u of t, it has the uh, Laplace transform. Okay, we write it by arrow, you understand. So it has Laplace transform, which is equals to 1 over s plus a, and the ROC for it is real of s should be greater than minus a. So for 1 over, we have now 1 over s plus 1, right? So if you look at the above equation, you can easily tell that here a is just 1, okay, because now we have this one and we have the ROC, which is s, and this is greater than minus 1. So it will have the because this produces Laplace transform of this, so that means here a is replaced with 1, so that means we can write it like e power minus t and u of t. Okay, so if we plot the graph for this one, the original signal, so that is x of s. So in case of x of s, we have two poles, one at minus 2 and the other one at minus 1. Okay, so the ROC for our signal is this one. If I just write the another part of the signal, which is minus 1 over s plus 2 and okay, so first because both the signals have the ROC as given here, that is the real of s should be greater than minus 1. So we can say, because based on the properties we have two parts, so the overall, because the signal consists of two parts, or let me write again on this slide. So that is the given signal x of s, which is split into 1 over s plus 1 minus 1 over s plus 2, and the overall ROC for this is real of s should be greater than minus 1. So if we see the ROC plot for this one, so we have, this is your sigma and this is your j omega, and you can see it has two poles, one at minus 2 and one at minus 1. So this is right-sided signal, right? So we have different ROCs for part 1. This let's call this one part 1. So in case of part 1, you have ROC which is same as the original signal, and we have, this is, for example, this is minus 1, right? So greater than minus 1 is your ROC, this whole part. Okay, for the second case, because based on properties of the ROC, the overall ROC for the two will be because ROC for this part, which is this one, right, it has a pole at minus 2, so ROC for this is all those points which are greater than minus 2, and for this part all those values where it is greater than minus 1. So that means the overall ROC for this will be those points that are greater than 1, because this satisfies the condition, right? So that means the second part, this will have the ROC basically this one, and this is greater than minus 2. Okay, so again by the similar argument we can say, because e power minus at u of t produces s plus a, and this where real of s is greater than minus 2. So if we have minus 1, right, you understand a is replaced here by 1. So if I replace by here, so you know there's this one, and here it was greater than minus a, so now it will be greater than minus 1. Similarly, this can also have the e power, it will be 2t, right, and u of t, and as discussed, the ROC for this will be real of s that is greater than minus 2. Okay, so that means the time domain signal of this one will be x of t, and x of t is equal to e power, right, because minus is here, so we can put a minus here, so that means e power minus t, right, and u of t minus e power minus 2t u of t. Okay, or you can take the u of t common, so you can also write it like this. So this is the time domain signal for the expression defined here, and I think that example also clears you that without knowing the ROC, this signal can have different time domain version, right? So because now we are given the ROC that's greater than this minus 1, so that means the first part has ROC this one, and the second part has ROC this one, and overall ROC for the both will be real of s greater than minus 1. So again we have the same algebraic expression as we had in the previous example, you can see, right? But now the ROC is changed, right? Previously it was RE of S, and it was greater than minus 1, right? So now we are given the same expression, but ROC is now this one, right? So this one indicates that it is the left side, right? So to solve it again, so that's partial fraction expansion. So I hope you understand how to use partial fraction. So because the same, everything is same, so I will not repeat it, but I'll just write the answer, and the answer is, we'll get this is the partial fraction expansion of 8. Now if we look at this one, we can say again it has pole. Okay, let me in fact draw. So this is, for example, your S plane, okay, and this is your real axis or sigma, and this is your imaginary axis or j omega. And if you look at the expression, so you can say that this expression, right, has two poles, one pole at minus 1 and one pole at minus 2. So that's minus 1 and that's minus 2, so it has two poles. Now by looking at the region of convergence, which is given as this one, so that means its region of convergence is basically greater than less than minus 2. So this is left sided at left half plane, right, left half of the plane. Okay, so that means if we again because the you know, for the left sided signal, we have done example something like this, e of minus 80 and okay, so minus e power minus 80 u of minus t. So it has the algebraic expression 1 over s plus a, and in this case, because this is the left sided, so we have the ROC real of s is less than minus 1, right? So if you compare with this one, so we can say that the first one, this is 1 over s plus a, so basically it will be, here we are replacing a with 1, right? So that means instead of because e power minus at u of minus t has the Laplace transform of 1 over s plus a. So that means if I have 1 over s plus 1, it will have the inverse, right, like this. The only difference is value of a. Here it's generalized value, right, and now we have 1, so it will be something like this. And again it will have, because it will have, if I replace a with 1, so if I replace a with 1, I will have the ROC for it will be real of s should be less than minus 1. Okay, so for the first part, if I just replot here, I have ROC, I have a pole at minus 1, and the ROC will be the region that is less than this pole. Okay, so that will be less than minus 1, so it is marked here. Okay, for the second case, again if we compare with the standard equation, this one, so we can say that a is basically 2. Okay, so if I replace here a2 also, so I get this one, right? So because using the ROC properties, you can see we have a signal that is summation of 2, right, parts. One has ROC this one, and the other has ROC this one, so overall ROC will be this one, right? That is real of s should be less than minus 2. Okay, so by just summing it, because this is sum of the two, so I can write that minus e power minus t u of minus t minus e power minus 2t u of minus t, or we can also, okay, so this is the solution for this one, or this is the inverse Fourier transform for the case. So you can clearly observe that although the algebraic expression are same, but with different region of convergence, we have different time domain signals, right? So these are this signal is now left-sided signal, right, that it exists from 0 up to minus infinity, whereas the same algebraic expression where we had ROC real of s greater than minus 1, so for that case we get the right-handed signal, right? So I take let's take the third example. Although we have the same algebraic expression, but now we have the ROC is changed, and in the first case ROC was, if you recall, ROC was let me write. Okay, so in the first case we had ROC that was real of s greater than minus 1. In the second we had, right, so in this case we got the time domain signal which is right-sided, that is from 0 up to infinity. In the second case we got the left-sided, and it was from 0 up to minus infinity. Again in this third case, x is missing here, so again in the third case we have the same algebraic expression, but we have the ROC, and that is defined by this one, right? So that means I can plot it here. Okay, so again it has two poles, one at minus 1. Okay, so for example this is minus 1, and we have another pole at minus 2. Okay, so now based on the ROC, this is your sigma and this is j omega, right? So based on the ROC given, we see that it is basically greater than minus 2 and less than minus 1, so this is ROC, right? So that means this one sequence is left-sided and the other one is the right-sided sequence. So although one is left-sided, one is the right side, so that means it extends from 0 to minus infinity and 0 to infinity. So it exists from minus infinity up to infinity, right? So which one is right-sided and which one is left-sided? That's important. How to determine. So if we look at the expression, so the ROC for the pole at -2 is right side, right? The ROC is right side to this pole, so that means the term involving pole at 2 is right sided. So that means this is the right sided, this one. Okay, this is the right sided. Similarly, if we look at the pole at -1, so the term that involves pole at -1, it has ROC to the left, right? So ROC for this pole is left side. So that means the term involving this is basically left sided. Okay, so the inverse of this will be e power right, minus e to the power minus t u of minus t. So this is left sided sequence signal, right? And this one is right sided, and you understand why this is right sided and this is left sided, because the expression for the Laplace for this one is this. Okay, and it has pole at -2, so it has pole at -2. Now given that the region of convergence is to the right of this one, you understand, from -2, so that's right side. So that's why it is right-sided sequence, so it will be something like this. And similarly again, although I have just to summarize, in fact, so if we look at this one, it has pole at -1. So if you see the ROC, so ROC is to the left side for this, so that means this one is left-sided sequence. So the overall expression is e power minus e power minus t u of minus t minus e power minus 2t u of t. So I hope this gives you the idea that depending upon the value of ROC, although the algebraic expression is same, but we have different signals, right? So the next topic is properties of Laplace transform. We'll not do the derivation because we have done so many in the while doing the Fourier transform, or in general the Fourier, so they are quite straightforward to derive. So the first property we are going to consider is the linearity, and you understand what is a linearity. So this topic you have done multiple times before. You understand the linearity says if x1 of t produces x1 of s and x2 of t produces x2 of s, then if I scale the two, the first one by a factor of a and the second one by a factor of b, so their transform should also be scaled by the same factor, and it will be the superposition, right? So you understand for linearity it is must that it satisfies the condition of the scaling, right? To scale the input, the transform should also be scaled by the same amount, and the other one is the superposition. If the input is superposition of these two, the output should also be the superposition of this, right? So in this case, we are more concerned with the ROC, or region of convergence. So the region of convergence in case of linearity is that ROC is at least the intersection of R1 and R2, right? So if R1 intersection R2 is empty, in that case we say x of s has no ROC and the signal has no Laplace transform. So let's consider an example because here we have used the word at least, so that means it can be minimum this one, intersection of the two, but it can be higher than this one, right? So for example, we have a signal which is composed of x1 of t minus x2 of t. Now the the Laplace transform of x1 of t is denoted by x1 of s, and its expression is 1 over s plus 1, and its ROC is the real of s should be greater than minus 1. Similarly, the second part, x2 of t, it has a Laplace transform equal to 1 over s plus 1 and times s plus 2. And it has the ROC, right? So that's greater than minus 1. Now, if I add them, right, because it holds the property of the Laplace transform holds the property of linearity, so that means the x of s will be basically equal to summation of the two. So x of s equals to x1 of s, which is 1 over s plus 1, and x2 of s, which is equal to 1 over, right, plus. So because it has a negative sign here, so that means we'll use the negative sign. So the output is basically equal to, or the overall x of s equals to 1 over s plus 1 minus 1 over s plus 1 into s plus 2. Okay, so if we look at this one, so if we have the ROC for the first one, this one, so it is something, it has a pole at -1, right? This is -1, and this for x1 of s. So it is pole here, and its ROC is the points greater than, right? This whole is its ROC, right? Similarly, for the second one, we have the same ROC, right? For the second part, x2 of s. Now let's see what we get from here. So if I simplify it, you understand its LCM will be s plus 1 times s plus 2, s plus 1 times s plus 2. Okay, so that means we just multiply this by s plus 2 and minus 1. Okay, so plus 2 minus 1, so I just do it here. 2 minus 1 is 1, right? So I just straight away write it as s plus 1. So I have this one. Now you see that s plus 1 cancels with s plus 1, so I am left with x of s. Okay, let me write here. So x of s equals to 1 over s plus 2. Okay, so because this is right-sided sequence already given here, so what will be ROC of x of s? So ROC of x will be it has a pole at -2, so I just write a pole here. It is at -2, so let's say this is the location of -2 where we have a pole. So if you look at this one and if you compare with the previous one, so you see it has ROC all this one, right? So if I take the intersection of this and this, it will be -1 to infinity, right? But now after the pole cancellation, because one pole is cancelled here, so now the overall ROC is greater than the intersection of the two. I hope this gives you idea why in general we write the ROC is minimum intersection of the two individual ROCs. So the next property we are going to consider is the time shifting. So if x of t has Laplace transform of x of s with ROC equals to r, right, then the shifted version of this one, so for example we shift it by amount of t naught. So if I shift it by amount of t naught, I get e power minus s t naught x of s, right? So it's exactly similar to what we had for the Fourier, if you recall those, right? And there's no effect on ROC. So that means time shifting a signal will have the same ROC as the original signal. So we can say that shifting in time domain does not affect the ROC. The next property is time scaling. So you understand if x, right, time scaling, you understand you scale the time by some amount of, for example, a, right? So if x of t has Fourier transform x of s, let me take the pointer. So if x of t has Laplace transform x of s and the Fourier transform resulting for the Fourier not the Fourier Laplace transform x of s, so the resulting Laplace transform has ROC which is equal to r. Now if I scale the signal by at, so x of at will have Laplace transform equal to 1 over a absolute x of s by a with, so the resulting changes in ROC will be, the new ROC will be equal to the r, the original ROC divided by a. So it is shown here in the figure that, so that's the original ROC, right? Now if the scaling factor is between 1 and 0, in that case we have ROC, the resulting ROC is stretch. So if you recall in time domain, if we have the scaling factor between 1 and 0, then the resulting signal is stretch. So stretching in time results in compressing in the Laplace transform. Okay. Similarly, if we have the a which is between 0 and -1, in that case the resulting signal will be compressed in time, and if you look at this one, it is stretched in the Laplace domain. The next property we are going to consider is the convolution property. So if we have x1 of t has the Laplace transform x1 of s with ROC equals to r1, and if we have another signal that is x2 of t and it has Laplace transform x2 of s with ROC equals to r2. So it's similar to the Fourier. If you recall that we had a property in Fourier that we said if two signals are convolved in time domain, then in frequency domain they were multiplied. So similarly we have, if two signals are convolved in time domain, so they are multiplied in the frequency domain. Okay, and the ROC will be the intersection of the two ROCs. Okay, so again you understand convolution is a very tedious one, right? It requires a lot of computation. So whereas comparing to the convolution, the multiplication is quite straightforward. So you can also, like you did in the we did some examples in the Fourier that multiplication convolution in time domain results into multiplication in Fourier domain. So what you do, you transform the two signals into Fourier, then multiply them, right? And then after taking the product, or for example, right, or if you want to find the impulse response, in that case you divide the output by input in the frequency domain and taking the frequency response and the frequency Fourier inverse of frequency response results into impulse response, which is quite straightforward if you compare it with the deconvolution. So similarly, we do the in case of Laplace, we can also do the same thing, and we find the Laplace of the individual signal, then we multiply them, we find the ROC of the resulting signal, and then again applying the inverse Fourier Laplace transform to obtain the product of to obtain the resulting signal. Again, like we said in case of the linearity property, convolution could be larger than the intersection, right? The ROC, the resulting ROC from the convolution could be larger than the intersection due to the possible pole zero cancellation caused by the convolution. So let's consider an example. We have x of s equals to s plus 1 divided by s plus 2, and we have y of s equals to s plus 2 divided by s plus 1, and this one has pole at right. So if we can, I think you understand. So if we plot the ROC for the first x of s, so ROC for x of s, this is your j-axis or imaginary axis, and this is your real axis or the sigma axis. Okay, so the first case x of s has pole at minus 2, so that means the ROC for this one is, for example, this is minus 2 points, so ROC for this will contain this whole region, right? So ROC is to the right of the pole. Okay, now similarly the ROC for the second one is because okay, we have a pole at minus 1, so this is minus 1. Okay, and we have ROC, which is this region. Okay, so if we take the intersection of the two ROCs, right, this one and this one, so the intersection will be basically this one. Okay, so maybe I can draw it again. So the intersection will be from pole at minus 1, and the ROC will be the region greater than minus 1. So this will be the ROC of the resulting signal if we take the intersection. But as I said earlier, that if there is any pole zero cancellation, then the ROC can be greater than the intersection of the two. So multiplying the two will result, you understand, into, okay, this is your y of s multiplied by x of s. Okay, this will result into, because two are reciprocal of each other, right? So that means s plus 2 divided by s plus 1 into s plus 1 divided by s plus 2. So the 2 cancels, plus 2 cancels with this, s plus 1 cancels with this, so we get 1. So 1 means it has ROC, which is entire S plane. Okay, so both the zeros are cancelled. Okay, we have, in the first case we have 0, right, at 0. Okay, denoted as z1, and it is equal to, at minus 1 we have 0, and we have pole. Okay, let me write it by p1, and it is at minus 2, whereas second one has Okay, let me call it z2. Z2 equals to minus 2 and p2 equals to minus 1. So this pole cancels this 0 and this pole cancels this 0. So the resulting product is just equal to 1a constant. So that means the ROC for this signal is the entire S-plane. Okay, this is your S-plane. So the entire S-plane is your ROC. So this is the properties of the Laplace transform table. So I hope you can go through them. We have skipped some of the properties and we have done some of the important properties. So I hope these are quite straightforward for you, because similar type of arguments and things we have done while we were doing the Fourier, right? So I think that's all for the lecture. Allah Hafiz.